All right, ladies and gentlemen, welcome back to section 3.4. We're going to finish up the tail end of the notes in your note packet for 3.4. We're going to start off by taking a look at example 4. Example 4 and 5 in the note packet deal with a couple of applications so you can see where these equations are used in real life situations. So compound interest is one that uses exponential equations a lot. So I'm going to use those as some examples so you can kind of see why it is we need to be able to solve some of the equations that we've been talking about up to this point. So let's go ahead and talk about example 4 here. And again, it's a compound interest problem. And kind of scroll up here. It's a compound interest problem. So we're going to need to recall some of those formulas that we talked about in section 3.1. So there was the compound interest formulas that we developed there. The first thing I noticed in this problem, let's just read it. It says, how long would it take for an investment to double if the interest was compounded continuously at 8%? So something that should stick out to you here is this compounded continuously. Right, so compounded continuously means that we're going to be using the compound interest formula, A equals P times E raised to the RT, the shampoo formula, right? PERT. Okay. And then we got to start going through the problem and seeing, well, what part of this equation is it that we are solving for, and what parts of the equation did they give me in the problem, so that we can start trying to find that missing piece. Okay, so one thing I noticed right away, I notice this 8%, so I know that R is equal to 0.08. Make sure you convert that percentage over to a decimal before you start using it in the formula. Otherwise, you'll get some incorrect answers there. Okay, so let's go ahead and start reading some other parts of this problem. Now it says, how long would it take for an investment to double? Okay, so the question here, what we're trying to find is how long, which is time, right? So t is the variable that we're going to be solving for in this equation. Now they want to know how long it would take for an investment to double. So we're starting with some amount p. They didn't specify the amount, but really it's not necessary. Okay, we're starting with some initial amount p, and when we're done, when we pull our money out of this account, we're going to have 2 times p, right? So in actuality, our ending account balance is going to be 2 times whatever p is. All right, so essentially I can take this 2p and I can plug it in here for a. So what I have is 2 times p equals p times e to the rt. Well, using a little bit of algebra from here, I can divide out a p on both sides, right? So the p's cancel, and what I'm left with is 2 equals e to the rt. And now I'm at a point where I can go ahead and start plugging in the information that I have. Okay, so we have 2 equals e, r is 0.08, and t is the variable that we're solving for. Okay, so this is why we've been studying how to solve these types of equations, because before, when we were dealing with compound interest, we didn't know how to pull this variable, right? The variable t, we didn't know how to pull this variable out of the exponent. There was no way that we knew how to solve that yet, but now we do. We can solve this. So what I'm going to do is I'm going to use one of the strategies that we talked about in the previous exponential equations that we've done. I'm going to go ahead and take the natural log of both sides. So I'm going to take the natural log of 2, and I'm going to take the natural log of e to the 0.08t. Okay? And once I do that, I can start applying the properties of logarithmic expressions, right? So properties of logarithms, one of which being the power property, right? So I'm going to write power property over here. And with the power property, that's going to allow me to take this exponent and put it in front. So now I can pull that piece down. Okay, so now I have the natural log of 2 equals 0.08t times the natural log of e. Okay. The next thing that we need to focus on here is this natural log of e. Hopefully by now you recognize that the natural log of e is just 1, right? So that part of the equation is just 1. So what I'm left with now is the natural log of 2 equals 0.08t times 1, which is just 0.08t. Okay, so now to get t by itself, I'm going to divide by 0.08 on both sides, and those cancel. And what we find is that t equals the natural log of 2 divided by 0.08. And this should get me an approximate amount of time in years, right? So whatever answer we get is going to be in the units of years. To double whatever investment I put into this bank. Okay, so I'm going to pull up my calculator and I'm going to go ahead and get an approximation so that if I were a banker and I had a customer come in and ask me this question, how long would it take me to double my investment here? This is the math that I would have to be able to perform to answer this question for them. Okay, so I'm going to hit the natural log of 2 and I'm going to divide that by 0.08 and hit enter. So it's looking like 8.66, right? Yep, 8.66. So 8.66 years. Okay. So it would take about 8.66 years to double our investment. Okay. Let's do one more. Example number 5. This will be a nice and short video. Okay, so in example 5, they tell us that we have $50,000 to invest, and you need to have $350,000 to retire in 30 years. Okay, so at what continuously compounded interest rate would you need to invest at to reach your goal? Okay, so first thing I notice, I'm looking for how many times the interest is compounded because that tells me which compound interest formula I need to use, right? We develop those formulas at the beginning so that we have those formulas at our disposal when they come up, right? So continuously compounded interest rate, right? So continuously means I'm going to be using A equals P times E to the RT, the shampoo one, okay? And it says at what interest rate, right? So we're looking for the interest rate. R is the variable that we're going to be solving for, right? R is located here in the exponent. That's what we need to find. So let's see how much of the other pieces of information we have. So notice we have 50,000 to invest, so that's going to be P, right? So P equals $50,000. And it says we need to have $350,000 to retire. So that means when I go to pull my money out of this account, I need to have 350,000. And I have 30 years to accumulate this $350,000, right? So T equals 30. So I'm going to go ahead and plug this information into my formula here. So A is $350,000 equals 50,000 times E raised to the R, I don't know what R is, times 30. Okay? All right, well, let's go ahead and isolate. Just like we've done before, we're going to isolate the exponential part. I want to get that thing right there by itself. So I'm going to divide both sides by 50,000. So they cancel here. We'll divide by 50,000 over here. And what we get on the left-hand side there is 7, right? 350,000 divided by 50,000 is simply 7. Equals, and then all we have left on the right-hand side is E to the R times 30. Or if you want, you could rewrite that as 30R. Okay, it might be easier to read. So 30R. All right, and then I'm going to use that technique that we learned about in the very beginning of this section of notes. I'm going to go ahead and take the natural log of both sides. So I have the natural log of 7 equals the natural log of E to the 30R. And then I'm going to apply the power property. The power property is going to allow me to move this 30R to the front of the logarithm. So now I have the natural log of 7 equals 30R times the natural log of E. Okay, doing good so far. So the natural log of E equals 1. So that one's going to drop out. So now we have the natural log of 7 equals 30r. And to get r by itself, I'm going to divide both sides by 30. So the natural log of 7 over 30 equals r. And I'm going to use my calculator to get an approximate for that. So let's see what we've got. Oop, didn't mean to do that. Here we go. Gonna move this over here. And we have the natural log of 7 divided by 30. And whatever comes out, whatever decimal we get, that's going to be your decimal form of the percentage for the interest rate. So whatever decimal you'll get out of this, you'll have to convert to a percentage rate. So here we go. So enter. So we get 0.064, so we'll say 0.065. And then converting that to a percentage, that would be an interest rate of 6.5%. So you would have to go to the bank and say, I need at least a 6.5% interest rate so that I can retire in 30 years. And good luck with that. So, all right. Hopefully that was helpful, and we'll practice some of those problems most likely in class. Thank you very much.